What's up, everybody? Today we're going to cover USACO's 2021 December contest at the bronze level. Problem number 2, air conditioning. Let's read it together. Farmer John's cows N, I think this means to say N cows. Farmer John's N cows are very particular about the room temperature in the barn. Some cows like the temperature to be on the cooler side, while others prefer more warmth. Farmer John's barn consists of a sequence of N stalls numbered 1 through N. Okay, so we're not going to have any skipping numbers. We're not going to have any duplicates, just numbered 1 through N, each containing a single cow. The ith cow prefers the temperature of her stall to be PI. Okay, so what that means, we've got cows in stalls numbered 1, 2, 3, 4, up to whatever N happens to be. For every cow, there is a preference for that cow. So PI, for example, in the case of cow 1, we'd be say P1. In the case of cow 3, we'd say P3. That's just the preference of cow 3 or the preference of cow 1. And right now the temperature in her stall is TI. That's the current temperature. Okay, so for example, in stall 3, maybe the cow in stall 3 prefers a temperature of 4 degrees, but right now the temperature is 6 degrees. Then what I would say is that if I equals 3, then the preference of I is 4, and then the current temperature of I is 6. So that's all these letters doing, is just giving symbols to refer to the different parts of this problem. What is the preferred temperature of some given cow? What is the current temperature of that cow's stall? In order to make sure every cow is comfortable, Farmer John installs a new air conditioning system that is controlled in a somewhat interesting way. He can send commands to the system, telling it to either raise or lower the temperature in a consecutive series of stalls by 1 unit. For example, raise the temperature in stalls 5 through 8 by 1 unit. Okay, so for example, if I have cows here, and let's say like cows 1, 2, 3, 4, and 5, let's say like this cow's preference is 3, this cow's preference is 2, this cow's preference is 5, this cow's preference is 4, and this cow's preference is 6. And let's say like the current temperature is 2, 1, 4, 3, and then 4. Then what I can do is I can say, if this is the current temperature, I can say, okay, raise the temperature in stalls 1 through 5, and then these numbers will become 3, 2, 5, 4, and then 5. And then I'd have to give one more command to raise the temperature in stall 5, and that would bring this up to 6, and then the problem would be solved. So we're able to do an entire sweep of stalls at the same time. The series of stalls could be as short as just a single stall. Please help Farmer John determine the minimum number of commands, fewest number of commands, okay, we want to do this as efficiently as possible, that he needs to send to his new air conditioning system so that every cow's stall is at an ideal temperature for its resident cow. Input format arrives from terminal standard input, so it's just going to be typed in input. The first line of input contains N. Okay, let's actually scroll down and look at the input. Here we go. Okay, so the first line of input contains N, which is this right here. That means there's 5 stalls. The next line contains N non-negative integers, P1 through Pn. That's just the preference of cows 1 through N. So this is the cow's preferences, 1, 5, 3, 3, 4, separated by spaces. The final line contains N non-negative integers, T1 through Tn. So this is the temperature the cows prefer to be at. Our output, which is also just going to be printed to the console, please write a single integer as output containing the minimum number of commands Farmer John needs to use. In this particular example, it's 5. Let's see if we can see why. The initial temperatures are 1, 2, 2, 2, 1, and we want to get to 1, 5, 3, 3, 4. The way they did that was first by increasing stalls 2 through 5. So that's this entire back half right here. Whoops, let me clear that up here. This entire back half right here got raised by 1 degree. So now you can see it becomes 1, 3, 3, 3, 2 on the next line. Increasing 2 through 5 again, that's these same stalls, which produces 1, 4, 4, 4, 3. 2 through 5 one more time, it's these stalls again, producing 1, 5, 5, 5, 4. Now the middle has gone too far. So in the middle stalls here, we're going to reduce 3 to 4, which is going to bring that down to 4, 4. And we're going to reduce those middle stalls 3 to 4 again, which is going to bring it back down to 3, 3, giving us our final answer of 1, 5, 3, 3, 4. Now there's actually multiple ways to do this. Let's look at another way to approach this, and understanding that there's multiple approaches is important. When they did this, they went past where the middle needed to stop in order to affect both ends, and then brought the middle back down. Let's look at what happens if we do that. Let's say, like, for example, I want to get everything to this line right here. If I have here, and then here, and then here, and then here, then if I were to lower the outside here to bring this all the way down. I could bring this one all the way down and this one all the way down to the baseline, but then these would be lowered and I would have to bring these back up. The amount of work that it takes to do that is exactly identical to the amount of work of doing them separately. Let's look at some examples of that. Let's say, for example, like I have, let's do 4, let's do 2, let's do another 2, and let's go back up to 4. Okay, so if I were to lower the first one here, let's assume that the middle is 0. If I have 4, 0, it'll be easier to work with zeros. 0, 0, 4. And I want to get these down so that everything is 0, which is this line right here. If I lower this side by 4, and then I lower this side by 4, that would take a total of 8 moves. If I lower the entire range by 4, then these will flatten out at the same time, but then these become -4, which would mean I have to raise them by 4 to get back. And then that still ends up being 8 turns. So whether you let the middle shift down together or whether you have the middle be completely separate and just do the ends separately, you get the same number of turns. So regarding this problem, there's a couple things that you need to do in order to approach this. One is you need to figure out how to simplify the problem and eliminate noise. One of the pieces of noise is the fact that we have this desired temperature and this current temperature. If my desired temperature is 15334 and my current temperature is 12221, then I've got all these numbers that have a different amount they have to go. And we would have to check each one of them to see whether or not they're above or below their desired temperature. But I can just subtract this right off the bat and come up with 0, 3, 1, 1, 3. And then this is sufficient because this is how much it needs to change by. And as long as I can figure out how to change by this much, if I can figure out how to turn this all into zeros, then that same set of commands would turn this into this. And the number of commands that it takes to go from one to the other is also going to be identical to the number of commands it takes to go back the other way. So it actually doesn't even matter if we solve from this one to this one or from this one to this one, because either way, it's going to be the same number of commands. Adding 3 is going to be the same amount of work as subtracting 3. So right off the bat, what we can do is we can get the difference between the two. And there's a lot of ways you can approach this as far as a programming standpoint. Maybe you want to load the first set into an array, and then as you're reading the next set, subtract it back out of the array. Maybe you want to create 2 arrays and then subtract them after you've loaded them both. But either way, we really only need the differences in order to solve this problem. Let's go over to the scratch pad here. So I've got 1, 5, 3, 3, 4, and then 1, 2, 2, 2, 1. And I'm going to subtract this. I need more space. And then I'm going to get the difference, which is 0, 3, 1, 1, 3. Okay, so let's look at some different kind of combinations of bars and figure out what we have to do in order to solve this. If I have a 3, for example, and then right next to it, I have a 2. 3, and then this is 2. The amount of work this is going to take to solve is going to be 3 steps. It's going to be 3 commands. The reason why is because the first command is going to cover both of them. The second command is going to cover both of them. And the third command covers only this one. And in fact, as long as we have sort of a waterfalling down shape, if I go 3, 2, 1, these are all going to just get solved by solving this first one, because this first one is going to require 3 commands no matter what, and we can extend those commands as long as we want. As long as it keeps descending, I can carry that command over. Now, if something steps back up again, for example, if I go back up to 3 here, down to 1, then with my first 3 commands, I'll have solved this first bar. This one's going to just get solved because it's shorter than that bar, so I can extend through it. And this one's going to get solved. Now, from here, I would have to stop one of my commands here and stop one of my commands here, which means this third bar is only going to get lowered by 1, which means the difference here, 1 to 3, is additional 2 commands that are going to be necessary in order to solve this edge right here. So if I were to start with, let's look at this again. If I were to start with numbers where they need to be changed by 3, 2, 1, and then 3, my first command is going to be -1 all the way across. That's this first command right here. That would give me 2, 1, 0, 2. Now, because of this, I can't, and I mean, I could, but then I would just have to subtract it going the other way, and we're trying to simplify. I can't raise this or lower this any further. Once this hits 0, that's considered done. So now I'm solving these two by doing -1, which is going to give me 1, 0, 0, 2, and then -1 again, which gives me 0, 0, 0, 2, and then I have to subtract 1 twice from here to get to 0. And that's essentially what just happened when I was drawing these lines here. Is that first -1 is going to go all the way across. That's this. The second -1 is only affecting the first two. That's the second -1. My third -1 is only affecting the first one. That's this -1 right here. And then I have, because this was only lowered by 1 and this was 3, that difference there is 2, and I have to lower it by 2 more. Let's look at that, how this works on the original sample data. If I take my original sample data of the 03113, clean up as best as I can here. Okay, with the 03113, 03113, actually, let me just clear this. 03113. Okay, so if I have 0 and then 3 and then 1, 1, 3. My initial one here that's 3, I'm going to need at least 3 commands to clear this. So this is from 0 to 3. That's a difference of 3, which means I need +3 commands, and that's going to carry over. This one here, these are going to get just solved together with that one because they're smaller than it, but they're still above 0. I get to this wall right here. This was at 1 and this is 3. That's a difference of 2, which means I need an additional 2 commands to take care of this. And then that would continue to waterfall if there were any further numbers, but there aren't. That's the end. So I've got 3 and 2, which is 5. And if we check our original case, then we can see that the sample expected output was 5. Now, the sample output didn't give you any hints, but there could be negative numbers when we do this. So let's look at how what that's gonna happen, because we can still use the same algorithm, but we have to do a little more carefully. Let's say like my initial temperatures are, just do 0, 0, 0, 0, 0 to keep it easy. And let's say like my desired temperatures are going to be 3. Actually, in order to let's do this. Let's make it 5, 5, 5, 5, 5, 5, 5, 5. Because I think they might have specified that we don't have negative temperatures, but we can have negative. Maybe they didn't specify no negative temperatures. Where's the range for temperatures? I don't think they specified what the range of temperatures could be. Oh yeah, here we go. Temperature values at most 100. Temperature values at most 10,000. They don't specify negative numbers, but yeah, we can create negative numbers just by starting at 5. So let's do that. So then I'm going to have 2, 7, 6, 3, 4. So I'm going to subtract these. 5 minus 2 is going to be 3. 5 minus 7 is going to be -2, -1, 2, and 1. Okay, so I've got 3, -2, -1, 2, and 1. So 3, -2, -1, +2, +1. Okay. So with the negative numbers, our rules get a little trickier because my change here from 0 to 3 is +3. But then here I've got a drop from 3 to -2. So how do we account for that? Obviously, I can't carry over anything from the 3 into the negative numbers. But this one definitely is going to have to go up by 2 by doing +2. That'll bring that one back up to 0. This one being negative is going to be partially carried by that. Because in the same way that they waterfall down on positives, if you lower this one's going to get lowered. It's going to be the same with negatives. If you raise the negative, the next negative is going to go up as well. Let's look at what that does. So when I have that -2 is going to carry through the -1 here, bringing us up to the 2. That's going to take an additional 2 commands to fix, and that steps down to 1, and that's free. So how do we account for all these? As it turns out, the easiest way to do this is actually just to get the difference of the numbers next to each other in sequence, and then divide by 2 at the end. So I've got my difference from 0 to 3 here. That's 3. I've got 3 to -2. That's going to be 5. I've got 2 to -1. That's 1. Absolute difference. I've got 1 to +2. That's 3. I've got 2 to 1. That's going to be 1. And I've got 1 back to 0. And that's going to be 1. I add these numbers together, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Divide by 2 equals 7. Let's see if we can organically do this in 7 moves and if that makes sense. Okay, so the 3 is going to have to be lowered by 3 degrees. That's 3. The -2 is gonna have to be raised by 2 degrees, that's 2. The 1's gonna just get fixed because of the -2 next to it being fixed. The 2 is gonna be lowered by 2 degrees, and that's gonna be 2. The 1 is just gonna get fixed. 3 plus 2 plus 2 equals 7. So essentially what you're looking at here is you're needing to extend that first idea of that waterfall into realizing what the differences are. The difference from here means that this is gonna have to be turned down by 3. The difference here means that if you were to turn down the range by 3, then this one's gonna have to go up by that much more. And essentially we're only doing half the distance because ultimately we're either turning up more or we're turning down more. And essentially what we're trying to do is we're trying to balance that out so that we can get everything back to 0. So just to kind of go back to the original problem here. Okay, so essentially what your code is looking to do is you have your input, you have your expected values, 1, 5, 3, 3, 4, 1, 2, 2, 2, 1. You subtract those, 0, 3, 1, 1, 3. Starting, and you probably want to put a 0 at the beginning and a 0 at the end to pad for this, because you need to get it back to 0. You go through, and anytime there's a difference, you figure out the absolute difference. From 0 to 3 is 3. From 3 to 1 is 2. From 1 to 1 is 0. From 1 to 3 is 2 again. And from 3 to 0 is going to be 3. We add all these numbers together. 3 plus 2 plus 2 plus 3 equals 10. And then divide by 2, giving us 5, which is our final answer here. All right, good luck coding it, and I'll talk to you in the next video.